Okay, so welcome to the course on analog and digital electronics. See, up till now, we have seen the basics and fundamentals of these operational amplifiers. And in the last few minutes of the last session, we have started with the some important parameters of operational amplifier, which are offset voltages and currents. Okay, so basically, what do you mean by these offset voltages and currents? See, when the two transistors of the input stage are not perfectly matched, then what is happening? The two base currents are different. Okay, and there is some difference between their base emitter voltages, and because of this, there will be a presence of unwanted voltages and currents, and these voltages and currents are called offset voltages and offset currents. Okay, so what are the kind of offset voltages and offset currents are available in case of operational amplifier? You need to study these offset voltages and current because they will create a nuisance in output, right? So what we need to do is we will try to null it out or try to reduce the offset voltages and current as much as possible. Okay, so this study of this offset voltages and currents is very much important because ultimately whenever we are going to design any analog circuit, at that time we need to take care of these voltages and currents. Okay, so we have started with input offset voltage, right? So what we have seen in input offset voltage, see, typically when both the input terminals of operational amplifiers are grounded, if we talk about the ideal condition, then in ideal condition, what should be the output voltage? Output voltage should be equal to 0. But in this condition, the practical op amp will always show a small non-zero output voltage. Why? Because of mismatching present in the internal circuit of this operational amplifier. Okay, and this voltage, whichever is present, though it is very much small in magnitude, but it can cause an error in the practical application, right? So to make such a voltage zero, it is necessary to apply a small difference voltage between the two input terminals of operational amplifier, and this input voltage is called input offset voltage, right? So it is nothing. If we talk about the definition of input offset voltage, then it is nothing but the differential voltage that must be applied between the two input terminals of an op amp to make the output voltage zero is called input offset voltage, and generally it is denoted by this VIOS, right? So this VIOS can be positive or negative. Hence, what will happen? The absolute value of the VIOS will be mentioned in the dataset. Okay, so if you wish to know the value of this VIOS, then it can be found from dataset of the operational amplifier. Okay, and it should be as small as possible because smaller the value of VIOS, better will be the matching of the input terminals. Okay, so we have seen many times the voltage to one of the input terminal is applied with proper polarity so as to null the output. Okay, and we are keeping another terminal grounded. Okay, so for ideal op amp, VIOS will be equal to 0, right? So this internal triangle indicates the ideal op amp for which we are considering the VIOS equal to 0. Hence, what will happen? The practical operational amplifier model will be like this. Okay, with the indication of the input offset voltage over here. And typically, the value of this input offset voltage, if we talk about IC 741, okay, this is the most widely used operational amplifier. For this IC, from the datasheet of the manufacturer, value of VIOS can be found is 6 milliwatt, right? So that was the input offset voltage. Similarly, you need to learn about the input offset current also. The second parameter you need to understand is input offset current. Okay, So the input stage of operational amplifier is, we know what is it? It is dual input differential amplifier, right? It is a balanced output, dual input balanced output differential amplifier. And these input terminals are nothing but the base terminal of the two transistors. Okay, we know very well, right? Let me try to draw it one more time. See, we do have these transistors, right? So we will be available with two different transistors. Now the base of these two transistors will act as an two inputs like this. Okay. This is our input number 1 and this will be my input number 2. Okay. And collect with this collector terminal we are taking some output. Okay, so if we are taking output between two collector terminals, then it is called balanced amplifier, otherwise it will be unbalanced amplifier, right? And emitter of both are connected to ground via some emitter resistance RE. Okay. So this is the case which we are available with, right? Now what is happening? The input currents of this op amp are the base current of these two transistors, Q1 and Q2. Let us say this is my transistor Q1 and this one is transistor Q2, right? So ideally what happens? Q1 and Q2 must be perfectly matched and two base current IB1 and IB2 must be equal. Okay, so there will be a flow of current IB1 from the base of Q1 and current IB2 will flow to the base of Q2. So ideally this should be equal, but as we know practically these currents are differing from each other by very small amount. Okay, not a very large difference but very small difference will be there, because whenever manufacturer will manufacture the transistor, he will try to match the characteristics, but because of the doping level, okay, the mismatching in the doping level of the semiconductor device, exactly matched characteristics are not possible, and that is the reason why the base current IB1 and IB2 value will differ. Okay, so if we take the algebraic difference between these currents flowing into the two input terminals of the op amp, it is called input offset current and it is denoted by IIOS. Okay, so mathematically if we wish to represent input offset current, then it is represented by IIOS is nothing but the difference between two base current IB1 and IB2. Okay, so here this IB1 represents the current entering into any of the terminal. It may be non-inverting terminal or inverting terminal. So let us say IB1 is the current entering into non-inverting input terminal, and this current IB2 is also the current entering into inverting input terminal. Okay, so if we talk about the ideal value, what should be the ideal value? Ideally IIOS should be equal to 0, but practically it is not equal to 0. And if I take the case of the most used IC, that is IC 741, then the value of input offset current for IC 741 is 200 nanoamperes. Okay, this is the typical value which you may find on the data sheet provided by the manufacturer, and this current is responsible to produce the output though input terminals are grounded. So when we have the input terminals are grounded, there will be a very small amount of current which is flowing through the two input terminals, and because of this output voltage appears at the output terminal. Okay, so this is the effect, not the effect, but this is the cause of input offset current. Similarly, we may have one more current which is known as input bias current. Right, so we already have gone through the definition of input bias current. It is nothing but the average value of the two currents flowing into the op amp input terminal. This is known as input bias current. Okay, so talking about the input bias current, it is denoted by IB, and IB is nothing but average of two bias currents, IB1 plus IB2 divided by 2. Okay, see, practically what happens, we have this operational amplifier with two inputs. One is the non-inverting input terminal, another one is the input inverting input terminal, and we are taking output over here. Now in this case what happens, I am grounding both the input terminals. Okay, and because of the mismatch characteristics of the transistor, what will happen, there will be a flow of current through base of these transistors IB1 and IB2. Okay, so this difference of IB1 and IB2 will cause input offset current. Okay, and the average value of this IB1 and IB2 will be known as input bias current. Okay, so mathematically we can represent input bias current as IB1 plus IB2 by 2. Now talking about the ideal values, definitely ideal values of bias current must be equal to 0. But practically there must be some value of IB current, and in case of IC741, the maximum value of base current is around 500 nanoampere. Okay, now see the difference. If I talk about the input offset current, then it will be equal to 200 nanoamperes. But whenever we talk about the average values of this gate current, at that time their value will be maximum 500 nanoampere. Okay, and this both the currents, both input offset current and input bias current, they are temperature dependent. They are temperature dependent. Okay, so we may find out the typical as well as maximum values of this offset voltage and currents. Okay, they will be available in the data sheet provided by the manufacturer, right? So this is the voltages and currents which are present at the input side of the operational amplifier, right? Similarly, we may have some offset voltages at the output side of the operational amplifier, and that voltage is known as output offset voltage. Okay? So we have one more parameter which is output offset voltage. It is denoted by VOOS, V suffix OOS. Okay? So the effect of input bias current, input offset current, and input offset voltage is to add the error to to the expected DC output voltage. Okay, these parameters which we have talked earlier produce the output voltage when both the input terminals are grounded. So what happens? The DC voltage which is present at the output terminals when both the input terminals are grounded, it is called the output offset voltage and denoted by VOOS. Okay. So if we want to define output offset voltage, then it is the DC voltage present at the output terminals when both the input terminals when both the input terminals are grounded. It is called output offset voltage, denoted by VOOS. Okay, so this output offset voltage caused by input offset voltage can be either positive or negative with respect to ground. Similarly, the output voltage due to the input bias current can also be either positive or negative with respect to ground. Okay, so if these output voltages are of different polarities, then the total output voltage will be very small. But if the output voltages are of same polarity, then the output offset voltage is large. Okay, excuse me for 1 minute. Okay, so we were talking about this output offset voltage. So mathematically, if we wish to write down the equation for output offset voltage, then it is the output voltage due to input offset voltage plus output voltage due to bias current, that is IB. Okay, so these two are the factors which will cause the output voltage when the input terminals are grounded, and that DC output voltage is known as output offset voltage. Okay, now all these parameters which we have seen are not desirable. Okay, so whenever possible, we should minimize this input offset voltage, input offset current, input bias current, and output offset voltage. Okay, why? Let us try to understand this phenomenon. Okay, so now what will be the effect of these parameters and how we will be able to compensate these parameters, that is of very much important, right? Because the effect of input bias current, input offset current, and input offset voltage is to add the error to the expected DC output voltage, and these parameters produces the output voltage when both the input terminals are grounded. Okay, this is the output offset voltage. Okay, so it is necessary to provide the necessary compensation to keep the output offset voltage to a minimum value, right? So some compensating networks are used in operational amplifier circuits to minimize the effect of offset parameters, and these methods are known as offset compensating methods or offset nulling techniques. Okay, so before we move on with these techniques, offset nulling techniques or offset compensating methods, let us try to understand what is the effect of this output offset voltage, bias current, etc. on the performance of operational amplifier. Okay, so first we will try to understand the effect of these parameters, and then we will try to nullify the effect of this parameter. Okay, so we'll start with the effect of input offset voltage input offset voltage on VOOS. Okay, So we have this input offset voltage VIOS. Okay, it is that voltage which must be applied between the input terminals to get the zero output voltage. Okay, this is required as the pair of transistors in the differential amplifier stage cannot be exactly identical. Okay, but the input offset voltage is very much small, of the order of few millivolt, that we know. Okay, now where is this input offset voltage? See, the input offset voltage is available at the input terminal. Okay, one of the input terminal, or maybe available at both the input terminals. So let us say this inverting terminal is grounded, and at the non-inverting terminal we are available with this input offset voltage. Okay, and because of this application of input offset voltage, what we are getting, we are able to nullify the output voltage. Okay, so we are making this output voltage equal to 0 by application of small input offset voltage. Okay? But because of this input offset voltage, what is the effect on output offset voltage? That is also need to take care, right? So the polarity and to which terminal it is to be applied, it is not fixed, and it is must be referred to the datasheet provided by the manufacturer, right? So for IC741 operational amplifier, we know that input offset voltage value is about 6 millivolt. This is the maximum value, right? And this indicates that the voltage at inverting terminal may differ from that of the non-inverting terminal by how much volt? 6 millivolt. Okay, this is the maximum voltage available, 6, and minimum is 0 volt. So what should be the difference? Difference will be 6 millivolt, and vice versa. If we increase the value at inverting terminal, then the difference is going to difference. Okay, so let us consider one typical circuit for the same, right? So we have one operational amplifier over here whose non-inverting terminal is grounded like this. Okay, and inverting terminal is also grounded. Okay. So this is my open loop configuration. Now I have told you that whenever we talk about the open loop configurations, they are not used widely. Okay, the most widely used configurations are closed loop configurations. Okay, so here we will consider one closed loop configuration, and this is my feedback resistance RF. Okay, this is my forward resistance, say R1, right? So this is the closed loop inverting, or you may say non-inverting amplifier with input voltage equal to 0. Here input voltage is not there, so V in will be equal to 0. Now what will happen? See, consider this as a point. Ideally, the current to the input terminal must be equal to 0. Okay, and here we are applying input offset voltage, and at this input terminal, output terminal, we are measuring the output voltage V0. Okay, so here you can see, if I talk about this non-inverting terminal, right? Non-inverting terminal is connected to ground. Okay, so basically it is at 0 potential, right? So what will happen to node A? Node A will be at this much amount of potential. What is it? It is VIOS. Okay, because there exists some input offset voltage because of the we have considered a practical operational amplifier. So though my input voltage is equal to 0, there will be input offset voltage available, and because of this, at terminal A, if you measure the voltage, it will be around VIOS. Okay, now let us try to find out the current flowing through it. Okay, so this is the condition. Okay, current is entering into the input terminal like this, and output voltage and current is fed back via this feedback resistor. Okay, so there will be a flow of current like this. Okay, now I'm interested in finding out this value of current. Okay, So current is flowing in this direction because of the potential difference at this point and point A. Okay. So at this point, what is the potential? VO, and at this point, potential is VA. Okay. So I will be equal to V0 minus VA divided by feedback resistance RF. Okay. But what is the voltage VA? VA is input offset voltage, that is equal to VIOS divided by RF. Okay. Now, what is this VIOS value? See, VIOS, you can see it is connected via this resistance R1. Okay. So if I talk about the voltage available at VA, it is nothing but I times R1. Okay. And this drop is nothing but input offset voltage VIOS. Okay. So the current flowing through it is VIOS divided by R1. Okay. So this is the amount of current I. Okay. Now put this value. Say this is my equation 1 and this is my equation 2. So put the values of equation 2 in equation 1. We will get VIOS divided by R1 is equal to V0 minus VIOS divided by RF. Okay. And now let us try to write down the equation in terms of output voltage V0. So output voltage V0 will be equal to VIOS into 1 plus RF by R1. Okay. So this is our output equation. And it shows the effect of input offset voltage on the value of output offset. Okay. So this input offset voltage produces the output, which is called output offset voltage. And this voltage not only depends on VIOS, but it also depends on the circuit components like RF and R1, as you can see. Okay. Now clear cut, you can see the output voltage, input offset voltage will have the effect on the value of output offset voltage, and this is the reason why we need to eliminate this input offset voltage, right? So ideally my output voltage equation should be equal to 1 plus RF by R1 into V in, right? But here in place of V in we have this VIOS. Okay, so this is the effect of input offset voltage on the output offset voltage. Okay? Now similarly, let us try to identify the effect of input bias current. Okay, because we have input currents also, offset currents also. So let us try to determine the effect of input bias current IB. So we already have seen earlier that the input bias currents are actually the base currents supplied to the transistors of the input stage to keep them biased in a linear region. Okay, and the circuit used to measure the input bias current is provided over here. Right? So we have this operational amplifier. Let us say this is my non-inverting terminal and this is my inverting terminal. Okay. This is the input voltage which is equal to 0. Okay. And there will be some current I. We are measuring our output voltage V0 over here and providing a feedback via a feedback resistor RF. So there will be a flow of current in this direction. This current is feedback current, you can say. Right? Let us say this is my terminal A and this one is terminal B. Okay, so there will be a flow of current IB1 over here and flow of current IB2 over here. Okay, so this is the operational amplifier in a closed loop configuration, right? Now consider when input voltage Vi is equal to 0. Okay, so what will happen? The output voltage V0 also must be equal to 0, but this is the ideal condition. Okay, practically both the input terminal, inverting as well as non-inverting terminals, will draw currents IB1 and IB2, right? So this current IB1 comes directly from the ground and it produces no voltage. Okay, I'm talking about IB1. You can see it is generated from this ground and it will produce no voltage. Okay, so neglecting the input offset voltage, the current IB2 will flow entirely through this feedback resistor RF. Okay, this is because both the input terminals are at zero potential and hence cannot input any current. Okay, so this bias current IB2 will produces a drop across this feedback resistance RF, which is nothing but the output voltage V0, because you can see it is directly connected to this output voltage. Okay, so this is because the left side of RF is at ground potential and hence practically instead of 0 volt we will get some voltage which is equal to V0 equal to IB2 times RF. Okay, so generally manufacturer will provide the values of this input bias current in the dataset, knowing the value of input bias current and the feedback resistance RF. Okay, so the effect of this input bias current on the output voltage can be predicted. Say for example, let us take the case of IC 741. Okay, so for this IC 741, what is the input bias current? Okay, input bias current is, we know, 500 nanoampere. Okay, and suppose feedback resistance RF is having value of 1 mega ohm. Okay, then what will happen to output voltage? Output voltage V0 will be equal to 500 nanoampere 10 raised to minus 9 into 1 mega ohm, 1 into 10 raised to 6. Okay, so upon solving this we will get 500 millivolt. Okay, so this is the output offset voltage without any input due to the effect of input bias current. Okay, so this input bias current of 500 nanoampere will cause 500 millivolt available at the output terminal V0 without any application of input signal at terminal 1 and terminal 2. Okay, so this is the effect of bias current. It will cause some output voltage though both the input terminals are grounded. Okay, so here you need to understand the key point of this is the input bias current changes the output voltage, output offset voltage by this amount IB times RF. This is because practically IB1 will be equal to IB2 and that is equal to IB. Okay, because these currents are very much small and this is the reason why we will consider this scenario IB1 equal to IB2 equal to IB. Okay, so now these two input offset voltage and input bias current will produce some output voltage which is known as output offset voltage. Okay, so suppose we are not using any compensation technique to nullify the effect of these offset voltages and offset currents. In that case we will be available with some output offset voltage and that total output offset voltage without any compensation is given by V OOS is equal to 1 plus RF by R1 into VIOS plus IB times RF. Okay, so this is the output offset voltage without any compensating network used in the circuit. Okay, so my actual output voltage should be 1 plus RF by R1, right, only into V in. But because of this input offset voltage and input bias current, we are getting this kind of output voltage, output offset voltage, and that must be nullified, that must be reduced. If we cannot nullify 100%, then it must be reduced. And this is the reason why we will require some compensation methods or compensation techniques. Okay, so let us try to derive these compensation methods. Okay, so first we will try to compensate input offset voltage, and then we will move on to input bias current. Right? So let us try to understand the compensation of input offset voltage. Right. So we know that the input offset voltage VIOS is the voltage required to be applied between the two input terminals in order to get zero output voltage. Okay. So for those applications where output must be at 0 volt when the inputs are at 0 volt, it may be necessary to include some form of DC bias at the input, which is capable of being adjusted in order to compensate for any offset. So to reduce the output voltage to 0, we use a circuit which gives us flexibility of obtaining input offset voltage of proper amplitude and polarity. And such a circuit is called input offset voltage compensating network. Okay, so before we apply external input to the operational amplifier with the help of an offset voltage compensating network, we will try to reduce the output offset voltage to 0. And then you can say your op-amp is null or balanced. Okay. So let us try to understand this offset compensation. Right. The offset voltage compensating network we need to understand. See, we will consider the case of IC741, where initially I have introduced some of the pin numbers, right? Basically, if we talk about IC741, then it is 8-pin integrated IC. Okay, so I have introduced you with some of the pins. Now today we will introduce another pin. Okay, so you can see this is my non-inverting input terminal and inverting input terminal. Okay, so non-inverting input terminal is pin number 2, inverting input terminal is pin number 3, and output pin is pin number 6, where we are getting our output voltage. Okay, so that is equal to 0 ideally when both the input terminals are grounded. Okay, now we need to provide some positive and negative supply voltage. Okay, so the pin at which we are providing positive supply voltage is pin number 7, and the pin at which we are providing negative supply voltage is pin number 4. Okay, so here at pin number 4 we are providing negative 15 voltage, right? So for many operational amplifiers, the offset compensation pins are provided to nullify this offset voltage. Okay, so the manufacturer's specification must be referred to use these compensation pins. Okay, so we have considered the case of IC741 where we have these two pins, say pin number 1 and pin number 5. Okay, so we have introduced this pin number 2, 3, 4, 6 and 7. Now today we will try to introduce pin number 1. This is my pin number 1 and this is pin number 5. Okay, so here I am available with pin number 1 and pin number 5. So in case of IC741, we will be available or manufacturer will provide these two pins, pin number 1 and pin number 5, and these pins are known as compensation pins. Okay, and manufacturer will recommend a 10 kilo ohm potentiometer that must be connected between this pin number 1 and pin number 5. Okay, so now let us try to connect a potentiometer of 10 kilo ohm. Okay, and then we will connect one wiper. It is connected to negative supply pin, which is nothing but pin number 4. Okay, so we will have one wiper over here which is connected to 10 kilo ohm potentiometer, right? So by adjusting this potentiometer wiper, we will be able to nullify the output voltage over here. Okay, so this is the arrangement of IC741 which is shown in this particular figure. Okay, now this is possible only when we are available with these compensation pins. See, in case of IC741, whenever we have this IC741, we will be available with this possibility. But in case if we have the operational amplifier from some other company which will not provide these compensation pins, in that case what we require some separate external compensating network. Okay, and we have to design this particular network. Okay, so suppose we are not available with this compensation pins, pin number 1 and pin number 5. In that case, we need to design a compensating network, right? So let us try to design a compensating network for such a case. Okay, so this is our general case where we have two input terminals. One is the non-inverting terminal. Let us say non-inverting terminal be grounded. Okay, so this is my V1 which is equal to 0 volt. Positive supply voltage is available at pin number 7, negative supply voltage is available at pin number 4, and output voltage is available at pin number 6. This is our load resistance RL. Okay, so this is the general case which we are available with. Now in order to get the output voltage V0 equal to 0, what we require is the compensating network. Okay, so here we will use one resistance. Let us say the value of this resistance is RA. Okay, and this resistance is being provided with the positive and negative supply. Okay, so plus VE is over here and negative VE supply is over here. Then we will use one wiper over here. Okay, let us say this is terminal T. Okay, and then there is one more resistance connected, and that is to be connected to non-inverting terminal. Okay, and we will have one more resistance connected to ground. Let us say this resistance be RC and this resistance be RB. Okay, so this is my complete offset voltage compensating network. Okay, this is offset voltage compensating network. Right, now let us try to understand the operation of this circuit. See, we have the voltage across this RC. Okay, so this is the voltage at the inverting terminal, that is this V2. Okay, now by adjusting the wiper on this RA, the voltage V2 can be made equal to voltage V1. Thus the input offset voltage can be made 0. and ultimately it will force the output voltage to be equal to 0. Okay, so here we will consider two cases. The one case is when the output is positive, and this is the case where V1 will be greater than V2. Okay, so when V1 is greater than V2, then V2 should be increased till it is equal to V1. Then and then output voltage will be equal to 0. Okay, so this is possible by moving the wiper RA towards plus VCC. Oh, sorry, this is VCC. Okay, not VEE. It is plus VCC. Okay, so when V1 is greater than V2, okay, consider this case. V1 is greater than V2. Then what should happen? We should increase the value of V2. And you can increase the value of V2 by moving the wiper toward plus VCC. Okay. And suppose we are available with the second case where V2 is greater than V1. In that case, we need to slide the wiper in toward negative VEE. Okay, so the design of such network can be obtained from Thevenin's equivalent. Okay, looking back into the resistance RA from this point T. Okay, so the maximum Thevenin's equivalent resistance will occur when the wiper is at the center position of the potentiometer. Okay, so we may call it R max, and R max is nothing but RA by 2 parallel RA by 2, which is nothing but RA divided by 4. Okay, and we know the supply voltages, these are plus VCC and minus VE, they are equal in magnitude. Okay, so the maximum equivalent voltage will be either plus VCC or negative VE. Okay, let us say we call it capital V only. Okay, so V max in this case will be equal to VCC or negative VE, and let us call it V only. Okay, so the compensating network with maximum Thevenin's equivalent resistance and voltage. Okay, so now let us try to draw this network as per Thevenin's network. So we will have one voltage source which will provide us the maximum value of voltage V max. Generally it is equal to V. Then we have the maximum amount of resistance. Okay, this is my point T, R max. And then after T, you can see we have resistance RB and RC. So we will have resistance RB over here. This is my terminal V2, and this is resistance RC, which is grounded. Okay, so this is our Thevenin's equivalent resistance and voltage. Okay, so here from this network we will be able to write the equation of V2. Okay, so V2 is equal to RC into V max divided by R max plus RB plus RC. Okay, and this maximum value of V2 will be the maximum value of input offset voltage. So we can write down this as VIOS. Okay, so we have different cases, and in different cases the values of this VIOS will be different. Okay, so this VIOS, now you can say, now depends on the magnitude of supply voltages. Okay, so let us try to understand this. See, we have this case RB is greater than R max and it is greater than RC. Okay, but what is the value of R max? R max is equal to RA by 4. Okay, so the bias currents for the op amps are small, that we know, and the voltage across RC is also very small. So the value of RC will be smallest. and that is what I have written over here, right? So the bias current and the current through RC are derived from the current RB, current through this resistance RB. Okay, so the current through RB will be smaller than the current through RA, and that will give us this scenario: RB is greater than R max is greater than RC. Okay, so now we know very well that RB is higher than RA. Okay, and this is the reason why we will get this R max plus RB plus RC is equal to, or sorry, approximately equal to RB. Okay, so in that case, if I rewrite this equation of VIOS, then VIOS can be written down as RC by RB times Vmax. Or what is Vmax? Vmax is nothing but V. Okay, so this is the equation of input offset voltage. Okay, so now the question is how we are going to design this compensation networks. Okay, so to design this compensating network, we will require the necessary steps to follow, which are known as design steps. Okay, so what are the design steps we need to take in order to design offset voltage compensating network? Okay, so let us go through these design steps one by one. First, we will try to identify the supply voltage, magnitude of supply voltage. This is nothing but V. So V will be equal to either VCC or minus VE. Generally, it is 12 volt or 15 volt in our case. Then second step, we will obtain the value of input offset voltage. Okay, so obtain the value of input offset voltage VIOS. Okay, from where we will get this value? From the data sheet of the IC. Okay, so now we know the value of V, we know the value of VIOS. Okay, so we will use this equation of VIOS to derive the relationship between RB and RC. Okay, so let us say this is my equation number 1. Okay, so we will use this equation 1, use equation 1 to derive relation between RB and RC. Okay, then we will select the value of RC. Okay, because we know the value of RC is generally very much small. Okay, and we will try to assume the value around say 100 ohm, right? So we will select value of RC generally very small. Okay, so it will be less than 100 ohm. Okay, so this is what we require. Then we will decide the value of RB now. Okay, so let us decide the value of RB. Okay, once we have decided the value of RB, now finally R max. Okay, so we will choose the value of R max, which is smaller than RB by a factor of approximately 1 by 10. Okay, so choose R max smaller than RB by a factor of approximately 1 by 10. Okay, and then as a final step, we will design the value of RA. Okay, design the value of RA from this equation of R max. Okay, so R max is equal to RA by 4. Okay, so these are the design steps which we need to follow, right? Okay, so this is how we will be able to design this kind of compensating network. If we are using IC741, then there is no need to design such a network because we already are available with pin number 1 and pin number 5, which are known as compensating pins. So only you need to connect one 10 kilo ohm potentiometer and one wiper, which is to be connected with pin number 4. Okay, so by adjusting this wiper on the potentiometer, you will be able to reduce the output voltage to 0. Okay, so this is how we will be able to compensate the effect of input offset voltage. Okay, similarly, we will try to try to design the offset compensating network for closed loop configurations also. See, in both these circuits, we have not been connected the closed loop. Okay, and it is the general tendency that we are using op amp in closed loop configurations only. Okay, so in the next lecture, we will try to cover the design steps for closed loop configurations. Okay, and we will see how we will be able to offset we will compensate the offset voltage networks, right? So we shall stop here. In the next lecture, we will continue with the compensation for closed loop op amp configuration, and then we will move on to input bias current compensations, right? Okay, so if you have any questions, then you may ask, or else we will
हेलो
stop.
सर.
Yes.
सर वो लास्ट वाला वीडियो